So what we're starting today is chapter 6. Chapter 6 is going to be over logarithmic and exponential functions. Logarithmic and exponential functions. And mainly today we're going to focus on more of the exponential part of this here. The first two types of exponential functions we're going to look at is exponential growth and exponential decay. Now we consider a function to be exponential growth where we have b to the x and the value of b is greater than 1. And with this here, when we have that value b greater than 1, as x increases, as the function goes farther and farther to the right, the function is going to increase faster and faster. If we looked at an example of this, we could just say y equals 5 to the x. This would be an exponential growth function. And a table of it with x values and our y. Well, when x is 0, we're saying y is equal to 5 to the 0. And anything to the 0 power would be 1. So when x is 0, the y value is 1. When x is 1, so we're looking at y is equal to 5 to the first power, which is just 5. So for us here, the x value is increased by 1. The y value is increased by 4. Let's say when x is 2. So we're looking at y is equal to 5 squared. Well, 5 squared, 5 times 5 is 25. So again, the x value is still increased by 1, but the y value is increased by 20. If we do this again with 3 and plugged it in, it'd go to 125, so it increased by 100, 4, 5, 2. It'd be 625. So as we see this here, it's increasing faster and faster. That's why we call these exponential functions, because it increases exponentially. So if the base is greater than 1, it's going to be an exponential growth. Now when the b value is between 0 and 1, we call it an exponential decay. It's going to decrease from left to right. Questions on this so far? And the interesting thing with exponential growth and decay is that this value, the b to the x, will not be 0. It has to be greater than it. So when we look at these here, we're going to do two things with these first four. We're going to say whether it's exponential growth or exponential decay, and then evaluate it for a given value. So if we look at y equals 2 to the x, would this be exponential growth or exponential decay? Growth, because the b value is greater than 1. Now when we evaluate it for a given value, we take that value and replace the x with it. So here it wants us to evaluate each one of these when x is 2. So we're saying 2 to the second power, 2 to the x. And 2 squared is 4. And with most of these here, we can plug them into the calculator. We can say 2 to the second power, and the calculator will tell us that it's 4. And it doesn't matter what value we have. We could say y, or evaluate it for when x is -3. Because all we're looking at is 2 to the -3rd power, which in our case would be -1, or not negative, it'd just be 1/8. 2 to the -3rd, 1/8. We can plug it in to evaluate it. Questions on A before we look at B? I just picked it. Yeah, we're just evaluating, because evaluating, we just plug whatever the value they want into it. Just giving another example. Any other questions with A? Let's look at B. Y equals 1/2 to the x. Would this be exponential growth or exponential decay? Decay, because 1/2, is it greater than 1 or between 0 and 1? Between 0 and 1, it's going to be decay. When the base is between 0 and 1, it's decay. When the base is greater than 1, it's growth. Now the second part is to evaluate this when x is 2. So we're saying y is equal to 1/2 to the second power, and 1/2 squared is going to be 1/4. Questions on A or B? Let's look at the next one. Y equals 1.3 to the x. Would this be growth or decay? Growth, because the base 1.3 is greater than 1. Then we can evaluate it when x is 2, so we're just replacing x with 2. So 1.3 squared is 1.69. Last one of these first four, y equals 1/3 to the x. So would this be growth or decay? Decay, because our base is between 0 and 1. And when we evaluate this for when x is equal to 2, so we replace the x with 2, giving us 1/3 squared, which would reduce or simplify to 1/9. Questions on this so far? Let's look at the next four. These here, they're not asking us to evaluate. They just want us to tell us whether they are growth or decay. So the first one here, 4 to the x would be. So y equals 4 to the x. Would that be exponential growth or decay? Growth, because the base is greater than 1. While we're over here, let's look at 3. F of x equals 0.25 to the x. Decay, because it's less than 1 and greater than 0. Between 0 and 1, it's going to be decay. Greater than 1, it's growth. 2, y equals 2/3 to the x. Would be decay. And lastly, f of x equals 1.5 to the x. Would be growth. Because 1.5 is greater than 1. Because if the base is greater than 1, it's growth, exponential growth. If it's between 0 and 1, it is decay. Then it's neither. Because if we had f of x equals 1 to the x, the graph of the function would actually be this flat line here. Because 1, no matter what the power is going to be 1. 1 to the 0 is 1, 1 to the negative. Even if we said 1 to the negative 4th, well, that's just the same as 1 over 1 to the 4th. 1 to the 4th power is still 1. So notice that 1 to the negative 4th is still just 1. Yeah, it doesn't increase, it doesn't decrease, it's just a flat line. It has to be greater than 1 or between 0 and 1. Negatives don't work for exponential growth or decay. The function's actually just all over the place. Mainly dealing with the properties of negatives and powers. Because as we looked at already, 5 to the x gives us this here. Or if we said negative 5 to the x power, well, it doesn't graph it. mainly because the number for the y value in blue, or if you look at blue and red, we do have similar values, but the red is switching from positive to negative. So it's actually jumping from one point to the other. It's not a continuous function. If we go 1, negative 5, 25, negative 1, 25, 6, 25. So it's not going to be growth or decay, especially if that base is negative. Questions on this so far? Now, the other number that we're going to deal with logarithms and exponentials is e. E is an irrational number, and we can approximate it by the equation 1 plus 1 over x to the x is the approximation of e. E is irrational. It is approximately, or it approaches 2.71828182846, and it just keeps going. But this base e is very helpful with exponentials and logarithmic functions.
Tristan Art, come to the office. Tristan Art, come to the office.
And one of the interesting things with e is we can actually treat it like a variable in a lot of cases. Because if we looked at e to the third times e to the sixth, when we multiply like bases, we add the exponent. So 3 plus 6 is 9. So e to the third times e to the sixth is e to the ninth. We can also divide them. 16e to the fifth divided by 4e to the fourth. Well, let's simplify 16 over 4. 16 divided by 4 is 4. E to the fifth over e to the fourth. When we divide like bases, we subtract. 5 minus 4 is 1, and if it's, is it bigger on top or bottom? So it would be 4e, or 4e to the first. Questions on this here? Because even though it is to the first power, we'd still write e, we just don't have to write the exponent. If you're typing this in the calculator, we wanted to approximate 4e, the calculator is going to want that first power, because it's going to assume there is a power attached to it. 3e to the negative 4x. So there's two ways to look at this. One, because since we're saying that it's squared, we're saying that it is being multiplied by itself. Being multiplied by itself, we're squaring it. Now we can just look at the multiplication. Well, 3 times 3 is 9. E to the negative 4x times e to the negative 4x. Whenever we multiply like bases, we add the exponents. When we multiply like bases, we add the exponents. So negative 4x plus negative 4x. Negative 4 plus negative 4 would be negative 8x. Questions on C? Do we see how that's done? Now, one of the nice properties with our powers of powers, really this would be considered a part of powers of a product. Power of a product states that m times n to the x is equal to m to the x times n to the x. We can apply that power to both terms. And when we have powers of powers, they multiply. Now notice this isn't m plus n. M plus n we actually have to multiply out. Because our factors we've seen constantly, we get those three terms, the middle terms, we have to multiply it out. So here, if we use that, I'm going to erase this so you don't have to rewrite it. Really, we could have said that we have 3 squared times e to the negative 4x times 2. If we can apply that power to both, with the negative 4x power, 2a power, they multiply. Well, 3 squared is 9. Negative 4x times 2 is negative 8x. We get back to the same spot. Questions on this here? And as a side note, because I know that y'all did the ACT prep boot camp the other day, and they do ask questions about properties of powers and exponents on the ACT. So, x to the 6th to the 3rd. Given this expression, simplify as far as simplified as possible. Well, there's two choices. We can either say that it is powers of powers, so it could be that it is 6 to the 3rd. It could be multiplied, could be added. I mean, there's different ways that we could have it, yes? But there's an easy way to check this. I'm going to say x is 2. Because if you do have one of these, we could say 2 to the 6th power to the 3rd, because that's what we started with, yes? 262, 144. So this should be 262, 144. So let's try 2 to the 6th to the 3rd. 2 to the 6th to the 3rd. Is that the same thing? No, so it's not going to be putting it to a power. The other was 2 to the 6th times 3. Is that the same thing? Yeah. Sometimes I can pick a number and check and see which one matches up. This one does, so that's it. So it gives you a way to kind of just verify, especially our properties of exponents. Is it simplifying the way it's supposed to? D. We will get to this especially, or more into this, in chapter 5. But radicals, what are the properties of radicals? If you have two or more things multiplied inside, we can split it up into different radicals, different parts. And the nice part about this is each part we can simplify in turn. Square root of 16, we know what the square root of 16 is, 4. And the reason it simplifies to 4 is because we're looking at the square root of 4 squared, yes? So square root of 16 is really, we're saying that it's the square root of 4 squared, which is 4, yes? We talked a little bit about it in Algebra 1, but especially in middle school math, y'all remember doing these. When the square root and square, if we have a square, they cancel. And that's about all we remember from them, yes? Okay. This was introduced a little bit in Algebra 1. We talked about it kind of like possibly like this here. The nth root of a is equal to a to the 1 over n. Or really we can say that the nth root of a to the x is equal to a to the x over n. We can rewrite radicals as fractional exponents. And this starts making sense and making things a little more understandable. So if we took this here, the square root of 4 squared, a is going to be 4. Our index, our n, with the square root would be 2. X in this case would also be 2. So really what we're saying is the square root of 4 squared is the same as 4 to the 2 over 2 power. Well, what's 2 over 2? 1. So really we're saying that we have 4 to the first, or 4. This is why if the index or the root we're taking and the exponent are the same, they cancel out. Because as a rational exponent, the square root of 4 squared is really 4 to the 2 halves power. 2 halves is 1, so it's just 4. Does that kind of make sense? And this is kind of nice. It makes why, it really explains why these radicals simplify the way they do. We don't teach it in middle school because it's a bit much to think of a fractional exponent at that point. But the reason I bring it up is because of this here, e to the 4x. Now the index for us is 2. So we could rewrite this e to the, or the square root of e to the 4x as e to the power 2 on bottom and 4x on top. And 4x divided by 2 is 2x. That's it. Really, we're just taking whatever the index is, the number in the radical. If it's not written, it's understood to be 2, and dividing it by that exponent. All right, let's look at the next 4. E to the 7th times e to the 4th is what? E to the 11th. 24 e to the 8th over 8 e to the 5th. 3 e to the 3rd. 24 divided by 8 is 3. E to the 8th divided by e to the 5th. We can subtract the exponents. 8 minus 5 is 3. Since it's bigger on top, it stays on top. But we have 8 of them on top, 5 on bottom, so 5 will cancel out with 5 of the ones on top, leaving us with 3 left. The next one, 10 e to the negative 3x. So we can apply the power of 3 to both, saying that we have 10 to the 3rd times e to the negative 3x times 3. Powers of powers multiply. Really, we have 10 to the 1st. Now, 10 to the 3rd. 10 to any power is kind of nice. The exponent tells us the number of zeros. Since it's 10 to the 3rd, we should have how many zeros? 3. 1, 2, 3, 1,000. E, negative 3x times 3 is, really we'd want to make that exponent positive, but we'll leave it as negative 9x. Last one, we're looking at the cubed root of 64 and the cubed root of e to the 9x. Now the cubed root of 64 is 4. As we're saying, what times itself? 3 times the 64. And that'd be 4. The e to the 9x, well, that's going to be the same as e to the 9x over 3, or e to the 3x. And again, we'll deal more with radicals and doing this, rewriting as a fractional exponent in Chapter 5. So that's as much as we'll see it about here. We'll see it, well, once more on the homework, but questions on this here? Now, e, this base e, can be an exponential growth or decay, but it's a little different because with e, we're looking at the exponent, not the base, because the base, e, is a set number. E is that irrational number, 2 point whatever. Now, if the exponent is positive, it's going to be growth. Because if the exponent's positive, we have this 2.718 to a positive power, so it's just the base is greater than 1. Now, if it is negative exponent, it's going to be exponential decay. And the reasoning for this is e to the negative x is the same as 1 over e to the x. That e is in the bottom of the fraction. And really dealing with the properties of exponents, we could actually say it's the same as 1 over e to the x. And some of the logic for why we can go from here to here, because if we did apply that 1 back to it, 1 over x, e to the x We already said earlier 1 to the x is just 1. So it's just going to be 1. It's not going to be changing no matter what x is. Which now, that base, 1 over e, is between 0 and 1. It is decay. We don't have to do all these steps. We just know that if that exponent's negative, it's decay. With e, if it's greater, if it's positive, it's going to be growth. So if we look at the first one, y equals 3 to the exponent is positive or negative? Positive, so it is growth. F of x equals e to the negative 0.5x. Would be decay. That exponent's negative. The next one indeed would be growth. Yes. 5 would be decay. And 2e to the 2x would indeed be growth. And that's it.